Example 7.2, we're going to use our rotational kinematic equations to analyze a problem. And it'll be the same problem-solving method we used for linear kinematics. So in this example, we have a wheel that's rotating with a constant angular acceleration of 3.5 radians per second squared. At the initial time, its initial angular velocity is 2 radians per second. So the first question we want to answer is, through what angle does this wheel rotate from time 0 to 2 seconds? So we'll use our familiar problem-solving method. We know alpha, 3.5 radians per second squared. We know omega initial, 2 radians per second. And we know the amount of time that's going to elapse. That's 2 seconds. And we want to find delta theta, change in angle. So we need to pick the appropriate equation to use from this list. And it looks like there's just one equation that will do the job. That's our third equation. So we can write our third equation, subtracting theta initial from both sides, as delta theta is omega initial t plus 1/2 alpha t squared. And we put in these values and find that the angular displacement is 11 radians. All right, so same method, just different symbols. Part B of this question asks, what is the angular velocity at 2 seconds? Well, we go through our method again. We know alpha, we know omega initial, we know the time. We also know delta theta now, because we just figured that out in part A. And we want to find omega final. That gives us several options, but I think the easiest one is the first kinematic equation. We could solve it using the second or fourth, but the first one will be simplest. So let's use omega final is omega initial plus alpha t, and you put in those numbers and you find it's 9 radians per second. Last question, part C. What angular displacement results while omega from part B doubles? So we have to think a little bit about what this question's even asking. What it's saying is that we have an initial angular velocity equal to 9 radians per second. and we have a final angular velocity equal to double that, 18. And alpha is the same value as it's always been, because in this entire situation, the angular acceleration is constant. And anytime you use the kinematic equations, the acceleration has to be constant, whether it's linear kinematics or rotational kinematics. They only work for constant acceleration or constant angular acceleration. All right, so we're given these quantities. We don't know how long it takes for this to double, so we can't use any time value before. We want to find delta theta. So it looks like there's just one equation that'll do the job, the fourth one. And you can solve this for delta theta. That will give you 34.7 radians. In the book, they actually ask you for the number of revolutions. So as one final step, you can turn this into revolutions, keeping in mind that one revolution is 2 pi radians, and that'll give you 5.52 revolutions. So the wheel spins around a little more than 5.5 times.